In this lesson, we learn how to find optimal solutions with linear programming. Here is our first example. An athlete desires to have at least 60 grams of carbohydrates, 100 grams of protein, and no more than 80 grams of fat each day. He considers 2 supplements to meet this need in the cheapest way. Tins of supplement A cost $20 and contain 20 grams of carbohydrates, 25 grams of protein, and 10 grams of fat. Tins of supplement B cost $30 and contain 20 grams of carbohydrates, 50 grams of protein, and 20 grams of fat. We first make a table listing these details. We have tins A and B, and they contain carbohydrates, protein, and fat. We also list their cost. Here are the values for supplement A. And for supplement B, we have the following. The constraints are given by the athlete's total daily requirements. He needs at least 60 grams of carbohydrates. So the total amount of carbohydrates must be greater than or equal to 60. He needs at least 100 grams of protein. So again, we put the greater than or equal to 100 in the protein column. However, the athlete can have no more than 80 grams of fat each day. Therefore, we put a less than or equal to 80 in the fat column. We can now generate constraint equations by labelling tin A as X and tin B as Y. Looking at the carbohydrates, we have 20X plus 20Y is greater than or equal to 60. For protein, we have 25X plus 50Y equals 100. For fat, we have 10X plus 20Y is less than or equal to 80. These 3 equations can be simplified by dividing all numbers in each equation by the same amount. The first equation can be divided by 10, so 20x becomes 2x, 20y becomes 2y, and greater than or equal to 60 becomes greater than or equal to 6. The next equation can be divided by 25 to obtain x plus 2y is greater than or equal to 4. We divide the final equation by 10 to obtain x plus 2y is less than or equal to 8. Finally, we write the objective function, which is an equation for whatever we want to maximize or minimize. For us, that is the cost. We write C equals 20x plus 30y. We now graph the constraint equation. We will do this by dividing the final number in each equation by the coefficients of x and y to find the x and y intercepts, respectively. So we have 6 divided by 2 equals 3, and 6 divided by 2 equals 3. We then connect these points. In the next equation, the x-intercept is found by 4 divided by 1, since we have 1x. This is 4. Then, for the y-intercept, we have 4 divided by 2 equals 2. Finally, we have 8 divided by 1 equals 8, and 8 divided by 2 equals 4. These are the three lines. Now we look where to shade. The greater than symbol in the first equation tells us to shade above the first line. We also shade above the second line. The third equation has a less than symbol, so we shade below this line. The feasible region is shown like so, between the lines where the arrows are pointing. To find the optimal solution, we substitute the x and y values of the vertices into the objective function. The vertices are the coordinates of the corners of the feasible region. So we have 0, 3, 0, 4, 2, 1, 4, 0, and 8, 0. Now we substitute these values in. In 0, 3, x equals 0 and y equals 3. So we do 20 times 0 plus 30 times 3, which equals $90. Next we have x equals 0, y equals 4. 20 times 0 plus 30 times 4 equals $120. Next we have x equals 2, y equals 1. 20 times 2 plus 30 times 1 equals $70. Then x equals 4, y equals 0. 20 times 4 plus 30 times 0 equals $80. Finally, x equals 8, y equals 0. 20 times 8 plus 30 times 0 equals $160. We are aiming to minimize the cost, and the optimal solution is $70, using 2 tins of A and 1 tin of B. Here is another example. We have small and large breakfast options. They contain eggs and tomatoes. We wish to maximize profit when these breakfasts are sold. The small breakfast contains 2 eggs, and so does the large. The small breakfast contains 1 tomato. The large contains 2. The small breakfast sells for $10. The large sells for $15. The constraints are formed by the total number of each item available. There are only 20 eggs that can be used. Therefore, the total eggs must be less than or equal to 20. We cannot use more than 20. We only have 12 tomatoes available, so again, we write less than or equal to 12. We also know that no more than 4 large breakfasts can be produced each day. This will give us another constraint that we will see shortly. We will call the number of small breakfasts produced x, and the number of large breakfasts produced y. Considering the eggs, we have 2x plus 2y is less than or equal to 20. Considering the tomatoes, we have 1x plus 2y is less than or equal to 12. Since no more than 4 large breakfasts can be produced, the value of y must be less than or equal to 4. We will now simplify the first equation by dividing by 2. We obtain x plus y is less than or equal to 10. The objective function is p equals 10x plus 15y. We now graph the lines. 10 divided by 1 equals 10, and 10 divided by 1 equals 10. 12 divided by 1 equals 12, and 12 divided by 2 equals 6. The last equation does not have an x-intercept. It is a horizontal line at 4. Since we have a less than or equal to sign, we shade below the first line. We shade below the following two lines also. Here is the feasible region, below all three lines. The vertices are at 0, 4, 4, 4, 8, 2, and 10, 0. When x equals 0, y equals 4, 10 times 0 plus 15 times 4 equals $60. When x equals 4, y equals 4, 10 times 4 plus 15 times 4 equals $100. When x equals 8, y equals 2, 10 times 8 plus 15 times 2 equals $110. And for x equals 10, y equals 0, 10 times 10 plus 15 times 0 equals $100. Therefore, the maximum profit of $110 is found by selling 8 small breakfasts and 2 large breakfasts. Visit mathsathome.com for further videos and practice.